Hello everyone, today I'm going to present my poster entitled Impact of Multipin Architecture on Electroluminescent Performance in Polymer-Based OLED Devices. In recent years, multi-layer organic optoelectronic devices have emerged as a key platform for light-emitting applications due to their low fabrication cost and high versatility in interface design. This work presents a proof of concept of light-emitting devices based on conjugated polymers, together with experimental results obtained from pin architectures fabricated under inert atmosphere conditions. Now, but what is an Oled? Well, an Oled is an organic light-emitting diode. It is a type of light-emitting diode in which the emitting electroluminescent layer is a film of organic compound that emits light in response to an electric current. The main characteristics of OLEDs are based on their ability to emit their own light pixel by pixel. This eliminates the need for backlight source. Some of its standout features are low fabrication cost, the solution processability, and mechanical flexibility. On the other hand, OLEDs are mainly used in displays and light-emitting systems. Its key applications include smartphones, high-end TVs, and decorative lighting panels. The performance of these devices stands out for their operational efficiency and long-term stability. Now, this is the methodology to manufacture a multi-layer polymer OLED. In this case, the device is built layer by layer to improve charge injection and transport to obtain uniform electroluminescent emission. Some of the layers are prepared under air conditions and others in air conditions, but is according to the layer that the device. Now, this is the functionalization of OLEDs. In this case, the operation energy levels of an OLED are based on the movement of electrical charge between two major energy boundaries called HOMO and LUMO. And the jump of electrons between these levels is what generates the light from the device. In this case, the LUMO is the lowest unoccupied molecular orbital. Its function as the conduction band. In this case, it receives the injected electrons. On the other hand, the HOMO is the highest occupied molecular orbital. It functions as the valence band. It houses the holes, is that to say, the absence of electrons. Now, in these materials, the cathode injects electrons into the LUMO level. The anode pulls electrons to the HOMO level, and here is the moment when the holes are created. Loads travel to the emission zone and they jump molecule to molecule. The electrons and holes are found in the emitter shell. They form a neutral state called exciton, and finally the electron falls from the LUMO level to the HOMO level. This loss of energy releases of a photon of light. Now, the architecture of these devices are the first layer is ITO, the second is P.PSS, REDF, ytterbium, silver, and the encapsulation to protect the device. According to this architecture, the results are represented in the CI diagram, where it's observed that the X and Y coordinates are located in the emission zone of the intense red color. Each device has a purity percentage above 99%. On the dominant wavelength is 611 and 614 nanometers. Also, the REDF have an emission near of 660 nanometers. In this case, the results obtained from the JBL course, it is observed that the device have a low current density and the turn-on voltage is less than 3.5 volts. In this case, the first examples has a luminance of 4,040 candelas per square meter. We could observe that the turn-on voltage is very low, but we need to improve some characteristics of exactly the turn-on voltage and the maximum luminance in each device. Now, the conclusions are the next one. First, REDF-based OLED devices showed high purity red emission, confirming that effective radiative recombination within the emissive layer. Second is that the electroluminescent performance indicates that ETL optimization remains necessary to improve charge balance. reduce interface losses, and enhance optical efficiency. Also, the device exhibits a higher turn-on voltage than commercial OLEDs. The multi-layer architecture has demonstrated an unstable operation and reproducible electroluminescent behavior. And finally, the obtained results suggest that multi-pin architecture represents a promising strategy for improving current distribution and charge transport in polymer OLED devices. This project has been elaborated with a collaboration between National Polytechnic Institute from Mexico City and the University of Valencia in Valencia, Spain. And that's it. Thank you for your attention.